Yes, thank you, Michael, for the kind introduction. So as you said, I've been working on multiple object tracking for a while, and today I want to talk about promising research directions. And in particular, I will have a first part of the talk about promising directions from the methodological point of view, and then I will briefly touch on the topic of data privacy. So let me start by introducing what is multiple object tracking. So probably most of you know some of these videos. We're focusing here on multiple pedestrian tracking because pedestrians are interesting as far as objects, and therefore tracking them is extremely challenging. And the goal of multiple object tracking is to detect and track all of the objects in the scene. So you do know what kind of objects you want to track, but you do not know where they are located. So classically, multiple object tracking has been tackled with the paradigm of tracking by detection, which means that you split the problem into two parts. The first part, which is called detection, in which you take any detector, FASTER, CNN, YOLO, or any of the newer detectors that are appearing nowadays, and you use it on each frame independently to obtain a set of proposed locations where objects of interest could be. And as you can see in this very easy example, there might be some error cases marked here in yellow, some false positives, some false negatives, or some badly located boxes. Now, in a second step, we want to do what is called data association. So from this set of proposed locations, what we want to do is we want to link them through time in order to create full trajectories. And of course, this becomes easier if we have all of the boxes in a frame, like for example, the blue trajectory, but it is much harder for the green trajectory where already in the second frame, there is no corresponding box for that particular pedestrian. So historically, and this is just data from methods published on the MOD Challenge benchmark, which is a benchmark that we have been running since 2014. And we recently analyzed all the methods that have been submitted to this benchmark and what kind of techniques they used to kind of see the trends of the community in trying to solve multiple object tracking. So you can see two interesting trends. One is that until 2018, people were focusing a lot on optimization for data association, going from more simple to more complex optimization methods. Another interesting trend is that motion models were very much in use in 2015-16, but later on they die out. And of course, there is the trend that has been also spreading in all of computer vision, which is using more and more learning to solve problems. And we see here the trend of tracking by regression, which is marked by these science stars, which has been appearing since more or less 2018, 2019, and is now dominating the challenge in terms of accuracy. But I want to kind of take a step backwards and go from this tracking by detection paradigm to the tracking by regression, which is now the paradigm that is dominating the scene in multiple object tracking. And for this, I'm going to talk about both parts that I've mentioned before. First, we're going to look at the detector, and then we're going to look at the second step, which is the data association. So how these trajectories are created from this detector. So probably most of you know or are familiar with FASTER RCNN. So in general, when I say FASTER RCNN, I talk about regression-based detectors. And these are the ones that take an input image, process it through a series of convolutions to obtain a feature representation. And then what they do is they analyze a region of interest, which they call the region proposal in that feature representation. And from there, they perform several tasks. One task could be, for example, classification, classifying the type of object that you can see in that region proposal. And the other more interesting one is regression. So what regression actually does, and this is going to be the interesting part for us, is that if you have a badly located bounding box, so as you can see on the left, this region proposal is badly located on top of the pedestrian. It doesn't really cover tightly all of the pedestrian, there is one arm out, there is a lot of space on the left. So what this regression head is going to do is it's going to regress the bounding box coordinates so that it tightly fits the object. And this is actually a very interesting method, a very interesting behavior that we thought, couldn't we actually use this for tracking itself? So what we proposed now already a couple of years ago is to use the detector for tracking purposes. And this is very similar to what we want to do in online tracking. So in online tracking, we have a rough position of the bounding box, and we want to adapt it to the next time frame and do this iteratively so that we can track the object through time. And so what we propose to do is we propose to do online tracking with a method that is trained as a detector, but has tracking capabilities. And therefore, we name it Tractor. So how this is going to work is we're going to go to frame, let's call it T+1. And I'm saying T+1 because I want to have already tracks from all the previous frames from 1 to T, so that I can go one step back to frame T and take my detections as proposals. So here what I'm plotting here are the bounding box of 3 trajectories that I have tracked from frame 1 to frame T. And I have these 3 IDs, the red, the blue, and the green. So now any online tracking method, what you want to do there is you want to tightly fit this bounding box to the new location of the pedestrian in this case. So what you want to do is you want to essentially perform bounding box regression, taking these boxes and tightly fitting into the new positions. And this is something that we can do with our regression head. We don't even need to retrain faster CNN for this. But now the question is, did this actually solve the tracking problem, or did we just fit some bounding boxes? And in order to answer this, we need to ask the question, where did my detection go in the next frame? So where did my detection, for example, with ID1, let's say that ID1 is the red bounding box, can I know exactly where did this particular detection go in the next frame? And since I can say this because I have correspondences, I know that the red box at frame T+1 corresponds now to this box here on the right image, which is tightly fit, and it doesn't correspond to the blue box or the green box. I can actually establish these correspondences, and therefore I can say that I have solved the tracking problem for these couple of frames. So of course, this is, first of all, a very easy paradigm that has quite some advantages. For example, we don't even need to retrain this regressor. We can use these extremely well-trained regressors that are trained for detection, and we get automatically well-positioned bounding boxes. We can also train our model if we need on still images. So let's say that now we want to track some particular type of cell for which we don't have annotations. It is much easier to annotate images than to annotate full videos. And another advantage, of course, is that Tractor is online. So you can use it for real-time applications if you actually have a regression-based detector that works online and works also in real time. But of course, this is a very simple model, so there are quite some disadvantages. First of all, the model doesn't have this notion of identity, right? So you have a bounding box, and everything that the regression is going to do is it's going to snap to the closest pedestrian in the vicinity, not to the pedestrian that you are tracking. So there is no notion of identity, but it's just going to snap to any pedestrian. So if you're trying to track in crowded spaces, it's going to get confused quite easily unless you have a really high frame rate. Of course, as any online tracker, the track is going to be killed if the tracker becomes occluded. That's not a major problem. It happens for any online tracker. And the thing is that we can actually solve these two problems with very common techniques used in multiple object tracking, like, for example, re-identification networks. So there's already tools in multiple object tracking to combat these problems. Finally, we have a third problem, And that is that when we have low frame rate or we have large camera motions, the box shifts by a lot in image space, and therefore the regression should also be trained to shift the box by a lot. But this is something that we try and it doesn't really work. The network cannot be trained for these large shifts, which means that we need to actually predict where the box will be so that the box is closer to the actual position where it should be regressed to. And this is something that we can also do with common techniques used in multiple object tracking, such as motion model, which actually predicts where the pedestrian will be in the next frame. So all the cons can actually be tackled with these two techniques that are used very much in multiple object tracking. And with this, we increment most of all the identity preservation. So on the third column, I show the identity switch, which for the vanilla tractor, they're actually quite high, above 5,000. While when we use re-ID and camera motion compensation, these identity switches are reduced by a lot. And also the accuracy, which we show here in the first column, is improved also by almost 2 percentage points. So with this, we got state-of-the-art results in 2019. But the most interesting thing about this, about our work, was actually, from my point of view, the analysis that we performed. Because what I was really surprised about is that we proposed this really simple method and we got state-of-the-art results. And therefore, we wanted to analyze what are all the other methods doing and why are they not state-of-the-art, in which scenarios are we better? Is our method better? And how can we, of course, further improve our method? So here what I'm going to plot is, first of all, in these thick bars, the distribution of occurrences in the ground truth. So you can see in the x-axis that we have the bounding box visibility, and we have a lot of boxes that are completely occluded, and most of the boxes are completely visible, between 90% and 100% visibility, which means that most of the cases, most of the tracking scenarios that we have in this challenge are quite easy because we can see the pedestrians with visibility 100%. And in fact, if we take the trackers in this particular scenario where we have 100% visibility, we see that most of the trackers are actually performing really well. So the percentage of tracked bounding boxes, which is what we plot here in the y-axis, is almost 100% for almost all trackers, which means that for these easy cases, everyone does well. But the interesting part here is the middle ground. So this visibility between 25% and 75%, in which all trackers start to suffer. So you can see that the performance really goes down, except our trackers, which are really keeping the performance at a quite higher level. So this is the range of visibility in which our tracker really shines compared to all other trackers. And the interesting thing is that for example, the graph methods, so the methods that, for example, build a graph on top of all the detections and try to assign them all into trajectories. You know, classically, people think that these methods are able to recover from partial occlusions because you're able to link detections from far away frames. But we can see here that this is not the case. They are actually not better at resolving these partial occlusions. And this is because you also have to be careful when you do these long-term links, because you could create a lot of ghost trajectories. So basically what we found out in our work is that the hard problems in tracking, so the coverage of large gaps in detections, recovering from partial occlusions, even if these occlusions are short, or tracking small targets, are still left unsolved. So most of the methods are just kind of fighting for these easy scenes and marginally improving these easy scenes. And in fact, we saw actually that in the last 2 years of mod challenge, so in the mod 16 and 17 editions, the tracking, the accuracy was only increased by 2.4 percentage points. 2 years to increase 2 percentage points, which means that people are really fighting for every point and not really solving the hard problems in tracking because, well, as the name says, these are really hard to solve and they mostly don't bring you any benefit in accuracy. So how we propose actually to move forward was, let's cover the easy scenes with Tractor, which basically means using the detector not only on a frame-by-frame basis, but use it with this idea that you're going to do regression-based tracking. Use basic ReID, basic motion model, and this will cover the easy scenes. And then tracking, the methods that actually do tracking can focus on the harder cases, on the long occlusions or on the extremely crowded scenes. So based on this paradigm, we said, well, now let's focus on the second part, right? So if we should focus on the harder cases, what kind of formulation could we use to actually tackle these problems? And so we took another look at the tracking by detection paradigm, right? We had our input frames, we had the object detections that now are going to be small tracks because we have Tractor. And before, people were focusing on frame-by-frame data association. And this is, so if object detection is something that we have already looked and we already know how to better leverage object detections, it's now time to go for the data association. So can we improve the data association part? And so we took another look at data association, and especially what we want to do here is we want to bring this idea of the community, this trend in the community of using more learning in solving the tasks. So can we also use more machine learning to solve this task of data association, which previously was tackled using optimization methods? So we go back to the formulation which was presented roughly in 2008. The formulation that used graphs to solve this data association problem. And in this formulation, what authors proposed were to use detections as nodes in a graph, and then to link these detections with edges. And finally, to solve this graph in order to predict what are the most likely connections between detections. And these connections are going to form trajectories. So for example, if I say that this pedestrian is connected to this pedestrian in the next frame, and in turn, it's connected to this pedestrian in the third frame, this means that all these three bounding boxes represent the same person, and therefore I can create a trajectory of this pedestrian in these three frames. So classically, graph-based data association was kind of separated into two parts. The part of feature extraction, right? So what kind of information am I going to put on the edges in order to express how likely it is that two nodes represent the same person? This could be some sort of similarity measure. You could put some learning in there. We had a work in 2016 where we had a Siamese neural network trying to figure out whether these two bounding boxes represent the same person or not. And once this information was inside the graph, then we would have a second separate step, which was a discrete optimization, which was basically solving the graph problem. And what we wanted to do now was we wanted to sort of switch a little bit this paradigm and say, can we go from detections to trajectories and perform this feature extraction step directly together with data association, right? So first of all, we want to encode this high order information that the graph has and that the separate feature extraction cannot have. We want to learn to perform this data association. And we also want to avoid this need for the expensive optimization. Although we will have a tiny optimization at the end, as I will say later on. So we name this neural network, as you might have imagined, that goes from detections to trajectories as our neural solver. So how this neural solver works is, first of all, we're going to have a step of graph construction. And this graph construction is going to put all kinds of information in the nodes and edges of our graph. In the nodes, we're going to have the representation of our bounding boxes. Therefore, we're going to have these tiny CNNs that are going to encode each bounding box into a feature representation. And for the edges, I will explain later on what kind of information we're going to have in there. Then we're going to have several steps of what we call neural message passing, which is the way to optimize these graph neural networks. And finally, we're going to have a classification problem, an edge classification. So which edges are active, which when an edge is active, this means that the two nodes that it connects, they belong to the same trajectory, and which edges are not active. So overall, this boils down to a classification problem. We have the feature extraction and a learnable data association. But the cool thing right now is that we link both problems and we can do backpropagation all the way through these steps. So we can basically learn to perform the best feature extraction for our edge classification problem. But for this, we need to work on this domain here, which is not the classic neural network domain. This is actually a graph domain. And for this, we're going to leverage what we call message passing networks. And the cool thing is that now we can work directly in this MOT domain, right? So the structure of the problem is going to be taken into account when we perform the learning. So just very briefly, the idea behind message passing networks is that in a first step, you create your graph with your node and edge feature vectors. You can imagine this as these small embeddings that contain some information related to the problem. And then the interesting part of message passing networks is this middle processing. And what this essentially does is it propagates information across the graph for several iterations. You can imagine every iteration as being a hidden layer in a classic convolutional neural network. But here what we're going to do is we're going to pass information from node to edge and from edge to node. So you can imagine that at each step of this information propagation, you have more and more information being passed from one edge to another edge, which is really far away, or from one node, one detection, to another detection that is really far away. So each detection is now aware of all the other detections around it, both in space and in time, depending on connections. So after this information propagation, this is the message passing step, then we have the classification. So our features have been updated with this information propagation, and now we can classify these edges into active or not. So the propagation step, very briefly, is divided into node to edge update and edge to node update. So the appropriate operations need to be defined for these updates, which are, again, not classic operations like you would have in a CNN. And you have to take into account, for example, that you don't know the number of edges connected to a node. So I also leave a link here in case you want to know more about message passing networks for mod. And these two updates, this node to edge and edge to node, are repeated for a fixed number of iterations called the message passing steps. And everything that we're going to do is we're going to update these embeddings that you see here, the yellow and green embeddings. We're going to update them with context information about the neighbors of a node and an edge. So just to briefly talk about what kind of information we put into these embeddings initially, that then, of course, it's going to be propagated. As we said, the bounding boxes are going to be encoded by CNN. So we're going to have image information in there. And the edges, of course, they represent connections between bounding boxes. So we want to have some information that cannot be seen from the image. Like, right, you can look at these two images and you can say, for example, how similar they are. And this is also in there in the form of a re-identification score. But we're also interested in knowing the relative size, the relative distance in image space, or even in 3D space if we have that information. And of course, the time distance. This all has to be encoded in the edge embedding through an MLP. And now the neural message passing happens, in which the nodes become in contact with the edge. They pass along this information, and this edge information is now updated, right? So the edge, which had previously only this information of size, distance, re-ID score, and time distance, now also has this information that is coming from the CNN. And so you can imagine that this MLP is going to update the information of the edge with, for example, how similar these two bounding boxes are. So all this message passing does is propagate information through the graph. Now, the edge to node update is a little bit more tricky, because classically what the edge to node does is it takes for a given node, let's say node 3 here in the middle, it looks at all of its neighbors, and it collects the information of all the edges that connect the neighbors. This information is aggregated through an operation, and then a tiny neural network updates the node embedding. But what we have here, and that is really specific for this problem, is that the nodes at time t+1 and the nodes at time t-1 are not really the same, right? We have this notion that some nodes belong together, which are all the nodes in t-1, and some nodes don't belong together. These are the ones at t+1. So if we do an update with all the nodes, we lose this separation, we lose this structure of the problem. And this is why we propose to do a time-aware edge-to-node update, in which the aggregation is going to happen separately for past nodes and future nodes. So again, what neural message passing does is it propagates the appearance, the geometry, all of this information that is contained into these edge and node embeddings. It just propagates it across the entire graph. And so you can imagine as this higher order information that is now present in each node and each edge of the graph. So before, each node was looking at itself, at its own appearance. Each edge was looking at its own connection. What are the two nodes that I'm connecting, but nothing else. And after this message passing, we have this higher order information also encoded in these embeddings. So what we're going to do now is we're going to do very simply edge classification, right? So we're going to fit these embeddings of the edges into an MLP, and this is going to predict whether the edge is active or not. Sorry. So this is basically very simple binary cross entropy. A couple of interesting points here is that, of course, our edge predictions come at a certain iteration of our message passing steps. So we need to make the iteration. We're going to have a weighted bunch active in edges, and this is because the problem is extremely unbalanced. A lot of inactive edges and very this we take into account in the loss. But most interestingly, something that really works for us here is that the sum over the last few message passing steps, so we take the loss for these last message passing steps, and we sum all of these losses. So we don't only take into account the prediction at step 12, let's say, but we take into account all the predictions from step 6 to 12, and we average them in our loss. So we don't want to just improve the last step, but we have a stronger signal for the loss by taking into account this accumulation of losses of the different message passing steps. And here what I'm plotting is quite an interesting graph in which we observed so how does the accuracy evolve as we use more and more message passing steps, right? Do we need to use 100 message passing steps, or are 2 or 3 enough? And what we see here is that for both accuracy as well as IDF1, which is this identity preservation measure, As we go from 0 message passing steps, which would be the classic discrete optimization, when we go from 0 to 2, this represents the highest jump in accuracy and IDF1 measure, which means that this is the point where you're starting to collect higher order information from the neighbors. And once you see what your immediate neighbors are doing, this is enough to already bring the accuracy quite a bit higher up. And from there, there is some improvement, but not too much. So this is actually very interesting to see. Like, of course, compared to vanilla Tractor, so this is, again, a method that we put on top of Tractor because we know already that these easy scenarios can be dealt with Tractor. So now we want to tackle the harder ones. And we see that most of the improvement comes in IDF1. So we have much, much less identity switches, right? Our identity preservation is much higher. And we also cover many more trajectories. So this is the mostly tracked measure, which measures actually how many trajectories are covered at least at 80%. And we see that we have a really high number here, indicating that we're really good at covering these small gaps, which are probably caused by occlusions or by lack of detections. And when we compare also with other graph-based methods, so these other methods have exactly the same potential as recovering from these small occlusions and bridging these small gaps because they have the same graph structure. But first of all, they perform more poorly, and also they are much, much slower because they have to solve this discrimination optimization problem, while we actually have all the processing power during training, and then at test time, this is really, really fast because it's only like a forward pass through this graph neural network. So overall, we saw that end-to-end learning for mod is, I mean, this is kind of our goal, right? And what we want to do in the future, following in this research direction, is that we want to further embed in our graph formulation the detection formulation. So kind of embed this Tractor paradigm into the message passing network. And of course, we have another problem, which are the really long occlusions. So with this formulation, we can solve for short occlusions, but the long occlusions would require that we have graph connections which go really far away in time. And this is still unfeasible because we would have then a huge graph that, for example, doesn't fit into GPU memory. So this is also not the ideal solution if we want to solve these really long occlusions where the pedestrian reappears after 100 or 200 frames. So after having talked about multiple object tracking, from the methodological point of view, I just want to briefly mention the topic of data privacy. And this is especially important for us because we have been pushing, as I said, since 2014, the mod challenge benchmark, which is a multiple object tracking benchmark. And interestingly, this benchmark started with these type of sequences, right? In 2015, 3 to 7 pedestrians walking around, really easy scene, nothing too fancy. And now we are here in 2017 dealing with this kind of scenarios. So first of all, as you can see, we have a higher frame rate, so we can actually do much more thorough analysis. We have all the occluders and all the other objects in the scene also annotated. And we have much more crowded scenes, much smaller pedestrians, overall, much harder cases. And for 2020, we envision these really crazy scenarios where we said, you know, we're going to take it to this really extreme level where even us as annotators have a tough time saying where each individual is in this scene. And in fact, just annotating this was a really tough task. But so you can see here the evolution from these easy cases only within this 5-year span. But of course, collecting this data makes you ask the question of what about people's privacy, right? So what about the image of these people that we're showing here? Can I actually collect this data? Can I use this data for research purposes and still keep people's privacy? So then we started looking into how people deal with privacy classically, like, for example, just removing the face, right? You can blur the face, you can put a square on the face, or you can do any operation on the face so that the person can no longer be recognized. But the thing is that if we do this, then the detection and therefore the tracking performance is going to be heavily affected. If we blur the face, we could still detect, for example, the person because there are the legs and all the other parts of the body. But if we now really want to anonymize the full body, we cannot just put a black box on top of the full body, because then, of course, any detector will not detect this as a person. So we want to have a method that actually anonymizes this image, anonymizes the face and anonymizes the body, so that we can still detect it as a person or as a face, but we can no longer detect it as this particular person that was walking around in this scene. And for this, our algorithm needs to have certain properties, needs to be, of course, anonymous. So you want to create a person that is not recognizable as the original one. It has to be realistic for a computer vision algorithm, which means that any person detector or face detector should still work. You should generate a new identity, have control over this identity, and I will briefly explain why. And also, we should have temporal consistency if we aim to do multiple object tracking on that. So one thing that, like, the first thing that comes to mind is the famous face swapping that has been going around now. But as we well know, doing this creates deep fakes, right? I don't want to put the face of, for example, a famous person all around this image, and then people will say, oh, this person was walking around this particular scenario on this day. This is completely fake, and this is not something that we want to do. And that is why creating this new identity that doesn't exist is really important. The control is also important if we want actually to deal with multiple object tracking, right? So we want these persons to be diverse enough so that we can identify as different persons and perform re-ID for multiple object tracking. And we also want to have control, for example, when we switch to different cameras. And I will tell you why later with an example. So I don't want but essentially, we propose to do this with generative new inventive faces that don't exist. And what a similar approach, but control process. So not only generating a realistic face, but generating a face that we can control over this so that the output is not only a new face, but it's a new face that we can control whether we want to have it the same for all the frames in a video so that we can do tracking or not. So why I talk so much about this control is that if I want to do multiple object tracking, I have to apply the same transformation to my image, right? So this control vector needs to be the same for all pedestrians in all the frames of this video. First of all, same for all pedestrians, because I don't know which pedestrian is which before I do tracking. So I have to choose this control vector here. I have to choose it once for the video, but I have to choose it to be the same for all frames. Otherwise, I will have a different transformation for every frame on the video, and I will not be able to perform tracking because the person will look different in every frame. But this gives me also the power that as soon as I switch to another camera, for example, if I want to avoid long-term tracking and potential misuse of the data, I can simply change the transformation. Another person will look completely different, will be dressed differently, and you will not be able to track it through different cameras throughout the city, for example. So I don't want to talk about numbers, but just show you a little bit some of the results that we have. So some look a little bit funky, but this is the source image that we're trying to anonymize. And on the different columns, you will see different types of anonymizations and the different control identities that we use to generate this anonymization. And this also works outside of the box with full bodies, even though the quality is a little bit worse because training data also has lower quality, and also works to obtain temporally coherent results. So for example, we have here 4 different anonymizations. This is myself being anonymized in 4 different ways. Only the face is being anonymized here, so not the hair and not the body. But you can see that the results are pretty stable. So there is a little bit of flickering, but you could definitely do re-ID between the frames and for example, track this face between the frames. So I now want to come to a conclusion for this talk. So I talk a little bit about methods that got us closer to end-to-end learning in multiple object tracking. And I'm really excited that, for example, we can reuse detectors much more than just the classic apply them on a frame by frame, so that we can solve all these easy scenes. And then we can work on the real hard tracking problems. And for this, we propose a solution in which we do learning in the natural mod domain, which is the graph domain. And this is shown to have quite some advantages, actually. But also on the other side, especially as someone who has been creating benchmarks for tracking for quite a long time, I really think that we should start looking into data privacy. I mean, now big data sets are very important for all kinds of learning algorithms. They are becoming very common, and there's a really hard potential of misuse. So we should really take a look at these issues also for mod benchmarks. With this, I want to thank you for your attention, and I also want to thank the collaborators from these works that I presented, and I will take any questions that you have now.